So we are Team HARP, and this is our Stat 199 final project on climate change markers and refugee flow. This is just a basic outline of the parts of our presentation, and so we'll start with the dataset introduction. So climate change is something that we know can influence daily livelihoods and eventually force people to leave their homes if it becomes severe enough. And trends in both climate change and refugee flow can be measured and have been by the World Bank. So we've acquired the World Bank data for the past 5 decades on many different climate change markers, as well as the number of refugees that left each country each year. And we focused our analysis on the Middle East and Central Asian belt, which is one of the 3 regions identified by the Institute for Economics and Peace as being particularly susceptible to the impacts of climate change. Next is our research question and hypothesis. Our primary goal in the project was to understand if and how predictors of climate change correlated with refugee flow from at-risk countries, focusing on the Middle East and Central Asian belt. And our hypothesis was at least one of the climate predictors, being CO2 emissions in metric tons per capita or other greenhouse emissions in kilotons, and land under zero production in hectares in the linear model would have a statistically significant relationship with refugee flow from countries in the Middle East and Central Asian belt. Next is just some basic exploratory data analysis. It was done not only to give a better idea of the variables by plotting their trends over time, but it was also done to exclude any unhelpful or simply invalid measurements from the final model.
As shown in the first graph here, the proportion of each country's total population that were refugees appears to have a somewhat erratic data that may be influenced by a majority of different factors. For example, Syria's refugee proportion rose significantly immediately following the start of wartime conflicts. It was clear that the refugee increase was due almost entirely to outside conflicts, and so Syrian data was excluded from the final model. The CO2 emissions graph shows that emissions have steadily increased for Iran since 1980. Emission trends have fluctuated in Iraq, but generally haven't increased since 1960. Pakistan has seen very slow increases, and Afghanistan has remained relatively constant. The methane emissions graph shows that levels in these countries were somewhat inconsistent throughout the years. For example, Afghanistan remained relatively constant, while Pakistan and Iran showed an overall increase from 1980 onwards. Nitrous emissions for Iraq and Pakistan have increased at similar rates over time since 1987. Emissions have fluctuated for Iraq and Afghanistan. As demonstrated by the arable land graph, the percentages of arable land available in each country remain relatively constant for all countries throughout the years. It is because of this finding that we opted not to include arable land as a variable in our linear model. Unlike the case for arable land, cereal land production did demonstrate some non-constant trends. For example, there is an overall steady increase in the amount of cereal land being utilized in both Afghanistan and Iran, although Iraq and Pakistan remain generally constant throughout the years.
In order to analyze if and how climate predictors correlated with refugee flow, we constructed a main effects linear regression model with log transformation. We also tested the model to ensure it satisfied the conditions for linear inference. And we constructed a linear model with interactions and tested for multicollinearity. Lastly, we applied our main effects model to countries in the Sahel region to see if it could be applied to other regions as well. The predictors used for a model were hectares of land under cereal production, CO2 emissions measured in tons per capita, nitrous oxide emissions measured in kilotons, and methane emissions also measured in kilotons. And the constructed model equation is shown on the slide above. The model developed for the Middle East region had an R squared of 0.7998, which indicates that about 80% of the variance in the proportion of refugees can be explained by the predictors used. And the adjusted R squared was 0.7923 to adjust for the extra predictors. And in order to test the effectiveness of our model, we compared the predictions from the model to the observed proportion of refugees in Middle Eastern countries. The following graphs are visualizing the predicted proportions of refugees in red and the observed values for each country in black. The linear model we created has varying levels of success with regards to accurately predicting refugee proportions for Middle Eastern countries. For example, in graph 7, the linear model was fairly accurate and consistent with the actual data aside from 2 outliers around the year 2000. whereas there was an extreme underestimation of refugee proportions for Afghanistan in the earlier years, as can be seen in graph 8. Graphs 9 and 10 also demonstrate the varying levels of success our linear model has with predicting refugee proportions for Middle Eastern countries. For example, as was the case with Iran, Iraq's linear model predictions were relatively accurate aside from one outlier. However, as seen with Pakistan, the linear model did not accurately reflect the true proportions of refugees in Pakistan, overestimating the proportion before 2000 and severely underestimating the proportion of refugees after this year. Overall, the predicted proportion of refugees based on linear model from the data of the whole Middle East is hit or miss for each individual country, with the model being representative for some of the countries and not as much for the others.
We then tested our model to determine if the conditions for inference were met: linearity, independence, normality, and equal variance. Graphs 11 and 14 demonstrate that the conditions for equal variance and normality were not met. However, conditions for independence and linearity seem to be met. However, as graph 12 demonstrates, the condition for linearity remains more questionable, and we address this in our discussion section. We then applied our model to the Sahel Belt region, which is another at-risk region identified by the Institute for Economics and Peace. We tested it on 2 different countries in the Sahel Belt with different conflict levels, Niger and Burkina Faso. While the model closely predicted the proportion of refugees in Niger, particularly after 1995, it overestimated the proportion of refugees in Burkina Faso over all years. We discussed these discrepancies in detail in our results section. However, this is likely due to differing levels of conflict and how closely our model predicts refugee flow in countries that have a higher proportion of refugees. So after testing our hypothesis, we observed statistically significant relationships for percentage of land under cereal production, metric tons of carbon dioxide produced, and kilotons of nitrous oxide produced. For each additional metric ton of carbon dioxide emissions produced per capita, the proportion of refugees decreases by a factor of 0.689 on average. This indicates that carbon dioxide had the largest effect of refugee flow of any of the climate change predictors we tested. Additionally, the adjusted R-squared value, as we mentioned earlier for our linear model with main effects, was 0.7923, which indicates that our linear model accounts for about 79% of the variance in proportion of refugee flow in the Middle East and Central Asian countries. We constructed a linear model with interactions, but found that it wasn't much different from our main effects model, and therefore didn't warrant further exploration. The model applied relatively well to all 4 countries. However, it underestimated Afghanistan, especially prior to 1999. This may be due to other factors such as conflict, political instability, persecution, or flaws in the model which are identified in our discussion section. The model had mixed results when applied to the Sahel Belt region, and this discrepancy may be due to the low number of refugees in Burkina Faso. This indicates that the model may be best applied to countries with significant refugee populations. And finally, the VIF score for every predictor in our model, except for carbon dioxide emissions, was really high, greater than 5. And this means that there's a high degree of correlation between explanatory variables, skewing the results of the model.
Most of our predictors did have statistically significant relationships with refugee flow. However, 2 of the conditions for inference were violated, and there's a high degree of multicollinearity, suggesting lacking statistical backing for these conclusions. And when you look at the direction of the relationship, some of them were obvious, like more land being used for farming led to less refugee flow. However, some of them were less intuitive, like increasing CO2 emissions actually leading to less refugee flow. However, this was likely due to economic development and increasing living standards, leading to fewer people actually leaving their countries and becoming refugees, which leads me to further investigation and analysis. On that point, we may want to look into socioeconomic factors and how those influence refugee flow. Moreover, it would also be wise to quantify the impact of conflict and other factors on refugee flow and use more robust data that disaggregates types of refugees and tests other nonlinear models. Moreover, the independence of refugee flow might also be harmed by the fact that some people decide collectively to leave a country, which would need to be addressed as well in future discussions and investigation. And that is the end of the project.